Hello everyone. So we are in the last lecture of chemical equilibrium. Literally this is the last lecture. Also there would be one more lecture on this chapter, but that is not any discussion over any topic. That would be on numerical problems. Okay, lecture number 13. So literally the lecture number 12 is the last topic where we are going to discuss degree of dissociation. Degree of dissociation, as denoted by alpha, this is the fraction of the reactant molecules which is decomposed. Suppose you have 100 number of molecules of A which is getting decomposed into new numbers of B. Now out of 100, 5 has been decomposed. Okay, 5 have been decomposed. So it is producing, suppose the value of mu is 2, then it is producing 10 number of B. Okay, so what is the value of degree of dissociation? Then the alpha should be 95 by 100, that means 0.95. Okay, now this thing can happen in two ways. Okay, it may take place at constant volume. Suppose you are taking such a gas jar with a piston where the piston is locked, it is not moving, so the overall volume is constant. So whether it is increasing or decreasing inside, the number of molecules actually increasing due to decomposition, the pressure increases. And if the piston is not locked, piston can move in the upward and down direction or in the right and left direction, then the volume is changing, the pressure is kept constant, the overall internal pressure is constant. Okay, so here in this case we are taking the pressure constant criteria, and temperature is constant in both the cases. Okay, it is common in both. Now if suppose the substance is decomposing, so due to that decomposition, number of moles within the cylinder is increasing, so the piston would move to the upward direction in order to maintain its pressure. Then the average density would decrease. So initially if it is 1 and 0, then the density should be rho 0, the volume should be V0, and molecular weight should be M0. But finally after decomposition of alpha fraction of the reactant, that means alpha is the degree of decomposition, then after decomposition the piston is moving but the overall mass is not changing and volume has increased. So mass by volume is density. So since volume is increased, so mass by volume would decrease. So this is the decreased density. The density would decrease. Even the average molecular weight also would decrease. Suppose you are taking 10 number of O3 molecules. So O3 decomposes into 3 by 2 O2. So the value of nu is here 1.5. Okay, suppose 2 numbers of O3 has decomposed to produce 3 numbers of O2. Okay, so initially the molecular weight had been what? Now 48 is the molecular weight of O3. So 48 into 10 divided by 10, so it is 48. But after decomposition of 2 molecules of O3, 3 molecules of O2 is produced. Then the molecular weight should be 8 into 48 plus 32 into 3. Oxygen has 32. So 32 into 3 for 3 molecules of oxygen, O2. And 48 into 8 for 8 number of molecules of O3. The summation is for 480, but you have to divide this, instead of 10, you have to divide this by 11 number of molecules. Because that overall number of molecules is now 8 plus 3. 8 number of ozone is undecomposed and 3 numbers of O2 is produced. So it is 11. So 480 by 11 is not 48. It is 46.363. Okay, so it is decreased. So this is M. So rho 0 is the initial density, rho is the decreased density after decomposition. V0 is the initial volume, V is the increased volume after decomposition. M0 is the molecular weight initially, and M is the decreased molecular weight after decomposition. Okay, So before decomposition, that number 10, 100, what I am citing as an example, this number is now n0, and this is equivalent to 1. Okay. So if n0 is 1, then what is the number of moles after decomposition? If this is 1, definitely 1 plus 0, it is 1, isn't it? Then what should be the value of n? It should be definitely the summation of these two, 1 minus alpha plus nu alpha. Okay, so it is 1 minus alpha plus nu alpha. And if you take alpha as common, then it becomes 1 plus alpha into nu minus 1. Okay, so this is the number of moles after decomposition, and this is the number of moles before decomposition. Now we have the ideal gas equation, PV equals to nRT. Here P is constant, T is constant, R is constant. So what are the variables? Only V and N are the variables, and they are found to be directly proportional to each other. That means V is proportional to N. So V by N is constant. So V0 by V may be written as N0 by N, as V1 by V2 equals to N1 by N2. So V0 by V is equal to N0 by N. Okay, now we don't know the value of N0 and N. Put these values. N0 is 1 and N is 1 plus nu minus 1 into alpha. So what is the value of V? Now the value of V is V0 into this term within the third bracket. Okay. Now what is the expression of density? Now density rho equals to weight of the gas or mass of the gas divided by volume of the gas. So if the same amount of gas is taken, then W is constant. In that case, rho varies as 1 by V. That means rho into V equals to constant, or rho 1 by rho 2 equals to V2 by V1. Conversely, rho 0 by rho would be equal to V by V0. So here we have written rho 0 by rho equals to V by V0. Okay, all are taking place at constant pressure. You have to keep in mind. Okay, pressure constant, temperature constant, volume is changing. Okay, what is the relationship between V and V0? Now this is the relationship. So in place of V we can put this value here. So in place of V we are putting this value V into within bracket 1 plus nu minus 1 into alpha. Okay, then V0 cancelled, then 1 plus nu minus 1 into alpha is left, and then rearranging this equation we can get another expression of alpha equals to rho 0 minus rho into nu minus 1 into rho. Okay, so here we are getting a relationship where alpha is expressed in terms of rho and rho 0. Okay. Okay, now the density terms rho and rho 0 may be replaced by the molar mass terms m and m0, as I have said previously. For the example of ozone, it was 48, now it is 43.63. Okay, so likewise this. Okay, so from the relationship rho equals to Pm by RT, density equals to Pm by RT, it is known to all of us. Here, which are the constant terms? Pressure is kept constant, R is constant, temperature is also kept constant. So P, M, M and the are the variables. So P varies as M. So rho 1 by M1 equal to rho 1 by rho 2 equals to M1 by M2, or rho 0 by rho equals to M0 by M. Therefore M0 by M equals to rho 0 by rho, and we know rho 0 by rho is what from the previous slide. Look, rho 0 by rho is equal to 1 plus nu minus 1 into alpha. So we put this value here, rho 0 by rho 1 plus nu minus 1 into alpha, and rearranging you get here the expression of alpha in terms of molecular weight. Okay, this is the expression. And we know the vapor density also. Vapor density into 2 equals to molar mass. We know this, isn't it? So m equals to 2d. So from that relationship, m equals to some constant into d. That means m varies as d. So m1 by m2 equals to d1 by d2, or conversely m0 by m equals to d0 by d. So d0 by d equals to m0 by m equals to, again we know the relationship, m0 by m equals to this one again, so this one, and by rearranging we can get the relationship alpha equals to d0 minus d into nu minus 1 into d. So the trend is same, rho 0 minus rho nu minus 1 into rho, m0 minus m nu minus 1 into m, d0 minus d nu minus 1 into d. So it is easy, very easy to memorize. Okay, now the piston is not moving. Okay, the pressure is increasing. So the density terms and the molar mass terms would remain unchanged. Why it remain unchanged? Because here V is constant. Okay, R and T constant as usual. Then P varies N. If P varies N, then they should have a relationship. N1 by N2 becomes P1 by P2. That means N0 by N becomes P0 by P. So we can write here P0 by P here equals to N0 by N, and this relationship is always applicable. So in place of N0 we are putting here 1, and in place of N we are putting here 1 minus 1 in 1 plus nu minus 1 into alpha, and by rearranging this here we get the fourth relationship of alpha. Okay, the fourth equation of alpha, and the equation is alpha equals to P minus P0 into nu minus 1 into P0. Here just the order is reversed. Here they had been rho 0, m0, d0, and here rho md, but now this is reversed. Here P minus P0, and this term is in the denominator. Okay, so nu minus 1 into P0. Okay, so this is also just apply some trick to memorize them. Okay, so that's all about degree of dissociation. Now time to just test your knowledge. How about you have learned this chapter, chemical equilibrium or thermodynamic approach? So in our final lecture, lecture number 13, we are going to give you some numerical problems along with their solutions. So till then, thank you and goodbye. Have a nice day.